Good morning, everybody. University Science Center Seminar. I'm pleased to have with us today Dr. Jonathan Peebles. Dr. Peebles started as a graduate student in Dr. Farhat Beg's group at UCSD, working on the acceleration of hot electrons and laser pre-plasma interactions. After graduation, he moved on to become a postdoc and eventually scientist in the experimental division at the Laboratory for Laser Energetics at the University of Rochester under Dr. Sean Reagan and Jonathan Davies. He is currently the instrument specialist for the magnetic field generating pulsed power device known as HEDS in the LLE and is the experimental PI for many campaigns related to externally applied magnetic fields. These include experiments on scaled laser-driven maglev, magnetized spherical direct drive, positron and electron confinement, and laser-driven coils. So today's seminar is being recorded, so if you're not comfortable with that, please log off. Also, please be aware it's an open meeting with people logging in from external to the laboratory. So please be aware of any export control issues. After Jonathan's talk, we'll take questions. You can enter your questions in the chat field and I'll read them. And otherwise, I hope you enjoy the seminar. Please take it away, Jonathan.
Yeah, thanks, Paul. So my name is Jonathan Peebles, and I'll be talking about laser-driven coils and how well do they work. What I'm showing for you on my title slide on the left is a sort of target type that you'll be seeing a lot of in the talk. It's a laser-driven coil. It's a sort of generalized configuration where you have a laser coming in through a disc attached and then through the disc and then hits a plate, another disc behind it, generating potential difference and drawing a current through a wire, which can generate a magnetic field. In the center, I have a result from Fujioka, who, as you can see in the graph, claims impressive kilotesla level magnetic fields, as shown in these sort of numbers at the top here. And on the right is some of the data I'll be getting to in my talk that we took using proton radiography, looking down the center of a laser-driven coil. And I'll be talking about how our results relate to those of other work. I'd like to thank my collaborators at the LLE, and I'd also like to thank the Office of Fusion Energy Sciences for supporting this work and the Center of Excellence for Advanced Nuclear Diagnostics and Platforms for ICF and HED Physics at Omega NIF and Z. So just an outline, laser-driven coils, an overview, then I'll talk about how well do they work, at least at first glance, and based on previous studies. Then I'll get into diagnostics, electric and magnetic field diagnostics, and then calibrating our own versions of those diagnostics. And then an overview of initial and follow-up experiments using those diagnostics to measure the electric and magnetic fields of laser-driven coils. And then finally, a bit of discussion and some conclusions from our experiments. So for an overview of laser-driven coils, I'm going to talk about the motivation and just general principles of operation as they're generally known. Strong magnetic fields open new avenues of research in high energy density physics and are highly desirable for inertial confinement fusion research. So LLE's magnetic field generator, also known as MyFEDS, is heavily subscribed for shots on Omega EP. And this is despite all the complications that it brings to campaigns. For instance, we had 8 shot days in Q4 of FY20 alone. So a lot of people have a lot of interest in using magnetic fields. Livermore is pursuing a project to create its own pulse power device that's compatible with the NIF cryogenic system and also their own debris requirements. They already have a warm pulsar, I believe it's the Warm Pulse Power Project, that's operating on the NIF. But pulse power systems, as they'll tell you, produce a lot of debris, and these debris are incompatible with many high-performing laser systems and experiments. So on the bottom left, what I'm showing is just a single shot of MyFEDS debris. You can see that Those tins were originally silver. They are coated in copper, and there's all sorts of other larger sort of scale debris beyond just copper deposition that is just unfavorable for a laser environment. And on the right, I'm showing a picture taken of one of the magnetized campaigns with a gas jet and two MyFEDS coils coming in. And you can see it's pretty crowded in this experimental setup in order to magnetize experiments. So there's a sort of catch-22 with magnetized experiments. Magnetized experiments a lot of times use high-intensity lasers to generate energetic particles for physics goals or to probe magnetic fields like proton radiography. And for that, you want high intensity and you want short pulses. So an intensity of over 10 to the 19 watts per centimeter squared and a pulse length of whatever the best compression is. When you have a pulse power device such as MyFEDS that can potentially damage optics, debris shields are then required. That drops laser intensities, for instance, on omega EP. That drops it at best compression below 10 to the 18. And if you want to get back up to 10 to the 19 watts per centimeter squared, you got to go to 10 picoseconds. Not only this, but the coils are typically bulky and they can block beams presenting physics goals. And basically what happens is magnetic fields are generated oftentimes at the expense of the rest of the experiment. There are a lot of experiments that you just can't do because to apply the field, you have to prevent doing some other critical component of your experiment. And on the right, I show an example of a radiograph with sort of the less intense beam that required a debris shield, drop the intensity. We really didn't get the most energetic protons that we could image with. Laser-driven coils are target-based platforms that are used to generate strong magnetic fields without a pulsar. So this is a sort of solution to this problem. Early laser experiments measured currents traveling through target support structures and into the chamber wall. So basically you shoot a target and then they were measuring outside, even in the chamber wall, they were measuring currents. And so while in these experiments current was low, it was hypothesized that basically electrons were ejected from targets, and this led to a neutralizing return current through the target. An example of this was shown here by Mario Manuel, who shot a sort of laser-driven Z-pinch and followed a current traveling down the stalk of this target, and he measured about 7 kiloamps of current with a large electric field. So basically, conventional laser-driven coils use a laser to drive charge separation, which draws a current to create a field in a loop of wire. And this solves a lot of problems by limiting debris that's generated, and you can provide magnetic fields to an experiment into facilities that don't have a pulse power device. So this is just a schematic and cartoon of how generally laser-driven coils function. And this was sort of pioneered as a concept in this paper by Dido back in 1986. However, I have to say something off the bat, and that's laser-driven coil experiments are often modeled after electronic circuits and are frequently referred to as capacitor coils. So this sort of nomenclature is all over the place in the literature. You have things being referred to as RL circuits. The target itself is referred to as a capacitor. And I think this leads to a lot of confusion because people see two plates and they assume that's a capacitor, but this is sort of a misnomer. Because if you went and took the physical dimensions of the plates and of the capacitor, the capacitance of such a thing is very, very small. And so, as such, the energy storage for such a capacitor is tiny, and it certainly would not be able to generate the currents that are seen in these experiments. So the way that we have to treat these targets is to treat the plates as current sources and not as capacitors, where you are removing essentially electrons from a plate. And in sense, removing electrons, removing charge is a current. Circuit theory also makes some certain assumptions, such as current uniformity, truncated circuit size, and it assumes Ohm's law. And these are assumptions that go into basically every experiment that has been done thus far. So how well do laser-driven coils work? Well, ongoing research it shows a lot of interest in laser-driven coils, in particular with coils producing kilotesla level fields. I mean, from articles, I just did a cursory search in the last year, and it's very commonly cited that you can reach kilotesla fields and use these for an experiment or used in simulations. Though I have to say that that kilotesla number is one measurement in a sea of experiments that have been performed on laser-driven coils and making magnetic field measurements. In particular, the highest field numbers I've circled here are from Fujioka, Law, and Santos. But you can see there's plenty of other measurements out there with varying fields. The amount of drivers is completely different across all the experiments. There's different coil designs, but these are the ones that are of greatest interest because they have the highest field. However, I think we have to take some of this with a grain of salt because the authors of the 1 kilotesla results in the paper itself declare that it breaks energy conservation, which somewhat throws suspicion on a lot of the results. So here's a chart taken from their paper. You have the Faraday rotation measurement, and then they also have a B-dot probe measurement. And the Faraday rotation measurements are measuring up to a kilotesla at 850 microns away. That's extrapolated if you go to inside the coil, that's extrapolated to 1.5 kilotesla. But when they did the integrated magnetic field energy calculation for this, they found that it was basically 15 kilojoules of field energy, which is far more than the laser energy. So we really should not be using this 1 kilotesla number as a reasonable, achievable field. And I think part of this is due to the fact that hundreds of Tesla aren't nothing. They're not insignificant. And in terms of field energy, because it's magnetic field squared, hundreds of Tesla are very significant. And so going to kilotesla requires quite a bit more energy. Even though you'd probably say 600 versus 1,000 Tesla, what's the difference? It's actually a huge difference. So 1 kilotesla, maybe not feasible. What about the 600 plus Tesla measurements from other experiments? So on the left, I have experiments by Law, who measured 600 Tesla using a B-dot probe and also proton deflectometry. And then on the right, Santos measured 800 Tesla for one of the coils, and then different coils had different measurements, and different diagnostic techniques had different measurements. And I'll discuss those in a little more detail. But basically, these had fields of over 600 Tesla. And to put that in perspective, my HEDS, which is 480 joules of stored pulse power energy, currently reaches about 100 Tesla with coils made as small as we can make them, which is magnetizing about a 2 millimeter cubed magnetized volume. And so we're talking about 6 times the energy or 6 times the field and 36 times the energy if you scale everything in terms of volume. So the field energy density provides some insight whether or not these quoted field values in applications are reasonable. Energy in the field is absolutely limited by the energy in the driving laser. I mean, we can't get more energy in the field than we put in the energy of the drive. Otherwise, we don't really need fusion, I guess. So field energy density is pretty simple to calculate. It's the integration of the field density squared over the entire volume. And in terms of magnetic field, this is also equivalent to the inductance times the current squared divided by 2. And just in general, lasers can deliver comparable energy as pulse power capacitors. So typical experiments are driven with a little less than a kilojoule of energy in terms of laser light. Pulse power capacitors typically store on the order of kilojoule or less when they're magnetizing experiments. So therefore, to be competitive with pulse power, laser-driven coils have to have one advantage to generate higher peak fields. And that's basically shrinking the volume that you have to magnetize. Magnetized volume can be made much smaller in laser-driven coils. That's partly due to the way that they're constructed. You have much finer wires, they can be made much smaller. And the field energy density provides some insight into whether or not, these are reasonable. So MyFETs, for instance, can typically have an efficiency of about 60%. if you go by peak field energy over the stored energy, and this is mainly just due to it not being critically damped. If we want to talk about laser-driven coils, finding the peak conversion efficiency is not very simple. First, you have to have a fraction of laser energy that's converted to hot electrons. You have a fraction of those that leave the plate. And then depending on how you model your laser-driven coil or how you believe it works, you have to determine what fraction escape backwards towards the undriven plate and what fraction of electrons are absorbed by the undriven plate. So you're going to have less energy available with a laser-driven coil to generate a magnetic field. And that basically means that magnetizing large volumes, such as implosions on if 4 millimeter size capsules, that sort of thing is not an option with a laser-driven coil. You just don't have enough energy available. And it's for that reason that nearly all laser-driven coil experiments that have been performed so far have coils with a diameter that's less than a millimeter. Sometimes they're like 500 microns. So these energy estimates indicate that some scrutiny should be applied to the 600 Tesla results as well. While these don't break energy conservation, they are pretty high in terms of conversion of laser energy to field. So for instance, in the law coils on the left, they require 290 kiloamps for 610 Tesla in the loop as described. If you integrate B squared and calculate the magnetic field energy in such a loop, just the wires and not really much of the disk or anything, because that's more difficult to calculate, you still get a conversion of laser energy to field of over 37%, which is, that's pretty high. Going to 800 Tesla for the Santos experiment, that needs 375 kiloamps, and that's over 50% conversion of laser energy to field. So I think some more scrutiny needs to be applied to these really high field values as well. Especially because those aren't the only experiments that have been performed. For instance, there's a range of results that have large differences between similar experiments. So there are experiments by Law and Courtois that have very different results, but they use similar diagnostics to measure their magnetic fields, but they have almost similar driving laser parameters. In this example, Courtois' loop was about 5 times larger, but they measured a field about 100 times less. And that 5 times larger loop doesn't account for that 100 times less field amplitude. So there's some gap in terms of what's being measured from experiment to experiment. Not only that, but even within a single experiment with different diagnostics, we get different results. And they can't all be true at the same time. So for instance, in the Santos experiment, there was one set of coils that produced 600 Tesla if you measured using the BDOT probe, 450 Tesla if you measured using Faraday rotation, and 95 Tesla if you use proton radiography. And so a more thorough investigation and comparison of diagnostic techniques is required. So now I'm going to talk about those diagnostics: BDOT probes, Faraday rotation, transverse proton radiography, and axial proton radiography. Certain diagnostics have difficulty in providing precise measurements of magnetic fields in the region of interest. In particular, I'm going to talk about BDOT probes and Faraday rotation in this context. Basically, if you want to measure in the region of interest, you have to place this sort of probe in the region of interest. So in the case of Faraday rotation, that's medium, a rotation medium, and then BDOT probe is just like the pickup coil loop. These would have to be placed very close to the magnetic field you're trying to measure. The problem is that these diagnostics pretty much immediately fail due to blanking or EMI when you place them very close to the interaction. So you can very rarely measure peak fields by placing these probes right in the region of interest. What you end up doing is you displace these probe diagnostics significantly, and then you extrapolate. So for instance, on the top right, I'm showing an image taken from a previous campaign by John Moody and Brad Pollock on EP with a laser-driven coil where they placed a Faraday crystal in the loop. And they were driving the coil from this side, and what they found was basically the crystal would start to blank if they drove it with more than, I think it was like 250 joules. And that was far less than the energy that they were hoping to drive it with. So they ended up putting crystals outside the coil and extrapolating inwards. Similarly, if you have a BDOT probe, so this is a typical RB130 probe that's used on a lot of these experiments, it's not only bulky, being a centimeter in size, but it's also typically displaced several centimeters from the region you're trying to measure. And it's not only picking up the loop, it's picking up everything else in the chamber. And that sort of thing needs some very careful extrapolation in order to get a proper measurement. So when you place the diagnostic far from a coil, you have a significant degree of extrapolation, and you also have an assumption of field geometry to begin with in order to make that extrapolation. So here I have the extrapolation that the Santos paper made, where they initially actually assumed if you had a perfect coil, they measured their signal all the way out 3 centimeters away, it would have said that they're at the center of the coil, they had 20 kilotesla. Now that's completely unreasonable, so they looked back at it, and they perfected the coil geometry in their extrapolation, and it turned into 800 Tesla subsequently. To give an idea of what kind of extrapolation we're talking about this. We're measuring 0.003 Tesla out here, and assuming that everything works out such that it's 800 Tesla over here. And this also assumes that you basically have no other sources for potentially putting voltage on your BDOT probe when it's sitting 3 centimeters away. Next, we have transverse proton radiography. This is much closer to seeing the region of interest. I mean, you send protons right through the region of interest, but due to the strength of magnetic and electric fields, you actually lose a lot of information. The idea is you have protons traveling transverse to the coil. So here we're looking at the coil, it's in plane, the loop is in plane, and the magnetic field is going across. I don't know if you can see my mouse, but the magnetic field is going across, and protons are deflected because they see the strongest portion of this magnetic field, and they create a void of protons. However, a void of protons doesn't necessarily tell you all that much about what's going on in the laser-driven coil. There's a lot of ambiguity in what causes the creation of a proton void, and electric and magnetic fields can duplicate features if you're not careful in a transverse radiography setting. So if you had a significant field, for instance, on your laser-driven coil, and it just deflects a proton immediately away, you really don't know what's happening going across the entire coil. You just know that there's a field strong enough to deflect a proton away. And another way to view this is to say that the transverse probe is actually just too sensitive if you're trying to make a measurement that's several hundreds of Tesla or even less. It would be way too sensitive to really measure the magnetic field. Like I said, if you can also reproduce features using magnetic fields with electric fields. So for instance, here I displaced electrons from a loop and then transverse probe them, and I can produce the same shape depending on, of course, how you structure your electric field. You can produce the same shape as a current would. So there's some ambiguity when transverse probing with regards to what field is causing what deflection. However, there is an obvious experiment to sort of discern what field is causing what deflection. That would be to reverse the current on the coil. If you have a transverse probe deflection, as we see, it looks like a sort of teardrop. If you reverse the current, that teardrop should flip, and you should be able to tell based on that reverse current how much deflection is caused from electric and magnetic field. However, I should say that I have not seen anything published that has attempted this pretty simple experiment. It's kind of surprising. Another thing to note for transverse probes is that magnetic fields typically require a lot more field energy to create the same sort of proton voids than electric fields. Some experiments, especially high-intensity laser ones, produce very large voids. And simulating large bulges with just creating them with an electric field or a magnetic field, typically you require a lot less energy to create the same void with an electric field setup than a magnetic field setup. And we can sort of infer that for a lot of high intensity interactions, when they see a large bulge, that they must be due to electric fields and not magnetic fields, because Otherwise, they would break conservation of energy because typically short pulse high intensity experiments have less drive energy. So yeah, attributing all deflection to magnetic fields very often produces an unreasonable energy conversion to current. So to address this, axial proton radiography can address all the concerns of transverse radiography for laser-driven coils. The idea is that you shoot protons down the axis of the laser-driven coil parallel to the primary field. The idea is that if you have electric fields, they're usually pretty symmetric around the wire material, and they cause protons to be focused or defocused. So on the right here, I'm showing what I have deflections from an electric field surrounding a wire and a magnetic field from current traveling along the wire, then combining them. With a magnetic field, weaker radial magnetic fields basically induce a rotation in the mesh. And this is somewhat not intuitive at first because you would say that, well, the protons are traveling parallel to the primary field axis. Why would you get any deflection at all? And that's because you basically have a radial field that's quite a bit weaker coming in because field lines are closed, and it changes signs as you pass through the coil, going from one side to the other. As you transit through the coil, there's a period where the proton is continuing on a trajectory and it leads to a displacement, and that shows up as a rotation. And then after it passes through the coil, it gets sort of kicked back to close to its original trajectory. And so you get a net rotation. And so when you have this, both the effects of magnetic and electric fields can be effectively decoupled from one radiograph. Not only that, you get some information on conditions on the inside of the coil. So if you have some asymmetries of field on your coil, then you can really detect that with this sort of probe approach. Whereas in the transverse case, all you can tell is that there's just a big void where protons aren't. So those are the diagnostics. Going into it, we want to calibrate and validate all of these diagnostic tools for use on our own experiments. So the first one is validating the axial probing of a MIFEDS coil, which confirms the functionality and provides information actually on the proton energy spectrum. What we did was we have a proton radiography setup shown on the left and a MIFEDS coil with a field going down it. The MIFEDS coil has 40 Tesla in the center, it's 50 kiloamps in a 4-turn coil. We probe it with protons and we can calculate ahead of time what's the expected rotation that we see for different energy protons. Higher energy protons will be deflected less, and so they have less of a rotation angle. So you can see here, this is the calculation going in. We estimate that the 5 MeV film should see a rotation of 18 degrees, and the 20 MeV film will see a rotation of 8 degrees. And this is a sample of a synthetic radiograph for 9 MeV protons deflected 13 degrees. Not only in doing this, we can also reverse the current of the MIFEDS coil, which is pretty trivial. We just put the wires in the other places when we hook it up. And we can verify this rotation in the other direction. So that's what we did. And we radiographed a coil in an inverted current. We measured the anticipated rotation. So these are both 9 MeV radiographs. These are showing the rotation of 13 degrees and minus 13 degrees. Everything looks exactly like we expected. Although I have to point out, what is this thing sticking out to the side? That's actually a bulging feature. That's a consequence of coils not being actually perfect when we wind them. We have a wire, we have a hole that requires an ingress and egress for the wire, where the wire is coming out of the plane of the radiograph. And so typically you would have current flowing through a wire going out here. This has a radial field going in this direction, and the force on the proton would kick the rotation this way. If we have a wire coming out of the board, you have azimuthal field, which causes a squeezing of the sort of protons, a force in this direction. And we can simulate that as well. We can stick a piece of wire vertically with the same current and show that it creates the same features that we see. We can actually also see this afterwards. So the benefit of hindsight, we can see that section of wire actually sticking out on that shot providing that extra sort of field, that azimuthal field that was kicking the protons in that direction. We can compare the rotation changes based on the proton energy to simulations and verify if this works. So here are the 6 radiographs from the same shot for different energies, going from 5, 7, 9, 10.5, 14.5, and 20 MeV, and their respective rotations. And they match up perfectly until you get to the very low energy, where basically the rotation stalls. There's no difference in the rotation between the first 3 radiographs. What that tells us is basically not that there's something wrong with our field, because it's very unlikely that we have a field that somehow doesn't affect 5 MeV or 7 MeV protons differently. What it tells us is that basically the first 2 films are dominated by shadowing from the protons that make it through to the 3rd film. What you're seeing is sort of the shadow of 9 MeV protons, some of which deposit their energy on the earlier films, on the film pack. And you're seeing them blurred with some of the lower energy protons. And so this actually tells us a bit about proton energy, and that we really, when we go into analyzing these radiographs, we really can't trust these first 2 radiographs, although they're blurred out to begin with anyway, so we probably wouldn't use them. We've also done some Faraday rotation on MyFEDS. We actually use this somewhat more often in the lab as a technique to verify fields on MyFEDS coils. So here's an example of a Faraday rotation test where we were validating the field for a 9 Tesla coil in the center. We placed a TGG crystal in the center and measured about 10 Tesla. That's because you're integrating over a millimeter of crystal, and the field increases as you get to the edges of the crystal. But the original TGG actually blanks pretty quickly in a laser environment. So going into Omega EP for experiments, we opted for fused silica. Going into BDOT probes, we designed a custom BDOT probe and constructed it and calibrated it for multiple shots on Omega EP. So here's an example or picture of the engineering schematic for the BDOT probe. We have 2 opposing loops at the tip that are a little less than a millimeter in diameter. They get taken out through SMAs and go to a balun and then to a scope of sufficient bandwidth. And we tested this in the lab. We have a little pulse power device that pulses about a 20 nanosecond pulse with a 3 nanosecond rise with a kiloamp current. We can actually move the pulsar around back and forth. It's on a stage relative to the probe, and we can verify the probe and its functionality and calibrate it. So here's an example of one of those calibrations. We have this 1 kiloamp pulsar. We can calculate what the field would be at the probe and compare that to what we measure. In white, I show the CVR measurement. It's a direct current measurement to current viewing resistor. In green, we have the raw BDOT data. So this is change in magnetic field over time. And in red is the scope integration of that green data. You can see that it matches up essentially perfectly during the pulse. But it should be noted that when you look later in time, it really starts to not match up at all. And what that is it's an electric field imparting a signal, and it's a very low frequency signal. And it's not very strong. You can't really see it on the BDOT probe, but it's there. And when you integrate it, because we're integrating a BDOT probe, it ends up being actually a very large signal as you go further out in time. And that's one of the tricky things about the BDOT probe, is that you're measuring electric fields, but you're integrating them, and it's not an EDOT probe. So you're integrating something that's not changing with respect to time. And that gives a pretty large signal and can really skew a lot of the results. I should say that sometimes this is filtered out with bandpass filtering, but as I'll get to in the actual experimental results with the laser, it's not clear whether or not such electric fields don't exist on short time scales. And in fact, I think it's pretty clear that they do. So now I'm going to talk about our experiments using these diagnostics. We had initial experiments and follow-up experiments, taking some lessons learned. So our initial experiments only tested the axial probe on different types of laser-driven coils. So we had double plate and single plate laser-driven coils. So you can see here on the left, single plate design is sort of just a disc with the coil and then a mass equivalent flag here. And the double plate is sort of the standardized design. We just send protons down the axis. What we found was basically we saw no rotation at all when we had a double plate. We tested a couple of different double plates. We had the sort of standard double plate target. We had a double plate where we put the stock on the other plate. And all of these didn't really show any rotation in the loop, which indicates that there's really no current above, I would say, 10 kiloamps. When we had the single plate shot, what we found was a lot of asymmetry. We basically could not reproduce the deflection seen with any symmetric magnetic or electric field. So you can see that there's no clear absolute rotation. It's not like it completely rotates inside here and you get a nice pinching around from the electric field. It's very asymmetric, and we needed an asymmetric magnetic and electric field to be able to reproduce these results. So why didn't the double plates work? The lack of double plate current is explained by the expanding plasma from both plates, which was measured by 4 omega probe and angular filter refractometry. Basically what happens is we have X-rays coming off the driven plate, and we're producing an indirect drive on the undriven plate. We can see this early in time, so at 300 picoseconds, we have the laser coming through the undriven plate, hitting the driven plate, creating plasma, which we expect. And then this undriven plate is being uniformly driven over its entire surface. And that would basically mean that you're getting a reduced voltage at best, if not no voltage difference, because you're ejecting electrons from both plates. If you go later in time, this gap is completely full of electrons. Electrons coming in from, if you can look very carefully, you can see there's sort of a structure that's like this. You have electrons coming from the undriven plate going this way, and you have the driven plate coming this way. It's just completely full of electrons, and also there's still just, there should be not really significant potential difference between the two plates. So no voltage difference, no current. So we think that this might be one of the reasons why the double plate doesn't work in our case. As a consequence, we have some new experimental goals. First, we want to verify the axial probing results by using multiple diagnostics on the same shot. That was just with axial probing, but we can compare that to transverse probing and the BDOT probe and Faraday rotation. The other thing is to try and remove as many sharp corners and burrs from the target as possible in order to reduce a lot of the electric field that we see. Previously, these targets were cut from laser cut from foil. That leaves a lot of sort of burrs, sharp corners, and knobbly bits. And we moved to a smooth magnet wire and foils. Previously, we used a sort of 5/6 of a loop with bends, similar to what other experiments have done. What we want to do is switch to just a U-shaped wire with half a loop, even though that's less field. We don't have any bends. It makes things a lot simpler in terms of analysis. Place the stock on the target on the opposite side of the loop from the plate for the single plate targets. So looking at this one, we have the stock connected to a flag, which is connected to a wire that's sort of seeing a similar electric field as the wire that's connected directly to the plate. So we wanted to make sure that this sort of effect of having the electric field of this interaction not affect what's going on the other side of the loop. So we'll see in a moment the change in the target that we made. Finally, we wanted to measure the current going in 2 directions on a single shot. So here we had 2 configurations with 2 types of targets. So it's really 4 total configurations that we used on the subsequent experiment. We have the double plate coil. So it just looks like headphones now because it's a U-shape. Here we have the double proton probing configuration. And then we have a Faraday rotation configuration. Here I'm showing the single plate coil, so you can see that we have the driven disc, a loop, a wire, sort of helical loop of wire going down to where the stock attaches. And the BDOT probe is placed pretty far away. It's about 2 centimeters from the loop. The transverse proton radiography of the single plate coils provided a very accurate current measurement. The single plate coils are really coiled stock is what you can treat it as. And it's a helix, and it provides basically 2 half loops and 1 target. So we have current from the driven plate down here, we have current going up, and then it's sort of looping around and then coming back down and then going up again. So effectively, we get to see the effective current and return current, or current and the reversed current on the same shot. We also have the axial probe, but due to target number restrictions, we didn't have any mesh for this. But we could just sort of see general sort of sheep-like structure and expansion from X-rays from the driven plate, which is over here. So to sort of give an idea of the geometry that we're looking at, we're sending protons down here. This is the transverse direction. And if you look from the proton's perspective, it sort of looks like a sine wave, but it's coming in and out of the page. So this is the orientation, and this is our radiograph. You can see that what we have is a bulge at one side and a pinch at the other. This is very promising for current because it's an asymmetric sort of effect, which is what you would expect if you have a current. If it's an electric field, you would expect a sort of symmetric effect, a bulge on both sides, for instance. But reproducing this radiograph, you only need 10 kiloamps of current. So here's a synthetic radiograph where I calculated a 20 MeV synthetic radiograph with 10 kiloamps of current. And we can match the deflections of the grid pretty well. You can see there's a bulge in the grid down here, bulge in the grid down here, pinch up here, pinch up here. The wire itself bulges, the wire itself pinches. So this reproduces it very well. And we were pretty certain that it's current because, as I said, the electric field would cause a more symmetric sort of effect on both loops. And you can sort of overlap it and see what the difference is between the calculated mesh deflection and the experimental one. And it matches pretty well. If you go to 20 kiloamps, for instance, then the pinching gets much stronger than what we saw in the experiment. And also, more clearly, I think the bulge gets a lot bigger than what we see in the experiment. So I think we can put at least an upper limit on the current measurement using this proton radiography of about 10 kiloamps. We also have the BDOT probe. What actually we found was when looking at the experiment, the actual piece of equipment that comes closest to the BDOT probe is actually the target stock and not the loop towards the target. So I am just going to be using a sort of very back of the envelope calculation for what we got from the BDOT probe. I should say these shots were done about a month ago, so I'm still post-processing some of this data. So if we attributed all the signal on the BDOT probe to dBdt, then what is the sort of upper limit that we can attribute to the field? So here's the integrated BDOT probe signal. We get about 0.3 to 0.4 volts. We have an attenuation difference, which sort of translates that to 30 to 40 volts if we're comparing to our lab calibration. Where in the lab, we measured 2.5 volts from a 1 kiloamp wire from 1.6 centimeters away. We have a tilt in the coil relative to the stock that's about 45 degrees. That would give a square root of 2 increase in the measurement, well, decrease that we have to account for. And then we also have some attenuation due to system bandwidth that I'm just going to have to assume exists in some form. I haven't done a full system bandwidth calibration yet. We've accounted for most of the equipment, but not all. And just back of the envelope calculation shows that we measure about 0.4 Tesla with the BDOT probe. And if you assume an infinite wire approximation, that translates to about less than 30 kiloamps in the stock. And that's really an upper limit that we measure with the BDOT probe. Should be noted that adding the short pulse for proton radiography and then running the BDOT probe introduces a significant signal that can't be a magnetic field. So here now I'm showing that same shot that I just showed, but next to it is another shot where we shot 2 short pulse beams about a nanosecond delayed. And you can see when the short pulse beams come in, they create a signal that's about 10 times higher. And if you were to, construe that as a current or a field, you would then sort of measure something like 300 kiloamps through the stomach. That would be more energy than a short pulse laser. Sorry about the dog. So clearly the short pulse laser introduces a significant electrical field component to the BDOT probe. And this is something that we really have to be careful about when making these measurements. We did Faraday rotation, and what happened was we basically measured no significant rotation in the fused silica media compared to other regions of the probe. The idea is that you split light into parallel and perpendicular polarizations. You split it close to 50-50, and then the Faraday effect in a medium with a refractive index causes a polarization rotation, causing more light to come in through one polarization versus the other. We could only do this with 500 joules in the drive due to blinking. When we went higher than that, we blinked the fused silica. But these are some of the data. So this is from the same shot. This is one polarization over the summed image versus the second polarization of the over the summed image. So you can see that, this was the sort of split on the experiment. We had 55% of the light going through on this polarization and 45% of the light going through on this polarization initially. And there is no difference in that ratio when looking at the fused silica rotation medium. I should say that there are some edges to it that show some changes of about 2%. So that maybe tells us a bit about the sensitivity of the diagnostic. Essentially, if we're seeing changes of 2% and we associated that with field, then we can estimate how sensitive we are to field for our experiment. So 2% changes in the relative intensity would correspond to shifts in the phase angle by about this much. That corresponds to about 1.5 degrees phase angle rotation, or about 1.23 Tesla when integrated over the 800 micron Faraday medium. This is because the crystal is sort of displaced from the main field, so it's only measuring, for instance, if you calculate from 10 kiloamp current going through the wire, it would only measure 1.66 Tesla out in the medium. So we can say that Faraday estimates basically about 7.5 kiloamps, but you have some pretty significant assumptions in there. So in summary, the single plate experiment basically tells us 10 kiloamps with proton radiography with a pretty high degree of accuracy. We can introduce electric fields, but I don't think it'll change the result much. The BDOT probe provides an upper limit, I would say, on the current of about 30 kiloamps. And the Faraday rotation says 0 to 7.5 kiloamps. So they're all pretty consistent. They're all basically in the sort of 10 kiloamp range. And what about the double plate? Well, the double plate, I would say, is even lower current. On the transverse radiograph, we have sort of two bulges that can be seen. We have this sort of large bulge, and then we have a pure proton void that's along the wire. I said 5 kiloamp current here. It's hard to say. There's a lot of electric field going on in this image that I'm still working through. However, when we look at the axial probe, we really don't see any rotation at all. Nothing over basically 10 kiloamps, what 10 kiloamps would have produced. So that provides an upper limit on the current that we measured. Looking at the transverse probe across different energies, they still require more analysis, but we know a few things. One is that for energies less than 15 MeV, we get this sort of bulge here. So there is some magnetic field that's likely to be there. And there's some focusing that's caused by a net electric charge. Electrons probably collecting around the wire. This electric field is about 10 to the 7, maybe less. Going from 20 to 30 MeV protons, you have this sort of void at the tip that's caused primarily by a small E and B field. And then at 30 MeV protons, there's really no effect on the coil. All you see is the coil. There isn't any significant field that does any deflecting. So For instance, this is the 36 MeV over here, and it just looks almost like a straight wire. There might be a slight bulge here. That might also just be the target. And so far, I've done some calculations, simulations, trying to reproduce this. I haven't got it quite right yet, but the best estimate that I have right now, and I'm still running them, is about 1.2 Tesla with 1.5 kiloamps. If you do anything much more than 5 kiloamps, you get a fairly sizable bulge here that we don't reproduce in the radiograph. BDOT probe measurements of the double plate showed very similar results, actually. We saw sort of 0.3 volt jump when the laser fired with less energy. This is with a 500 joule shot, and basically we saw essentially the same signal. So we had the same sort of limitation of the current must be less than 30 kiloamps according to the BDOT probe. I should also note that if you look at the raw data of the BDOT probe, it becomes quite a bit less convincing. This is what that same data looks like when you don't integrate it. And this is really the stuff that's leading to the signal that we measure. But you get stuff out here as well. I would take BDOT probe data with a grain of salt. And just a summary of all those results, basically, really the proton radiography tells us that we have almost no current. And the axial probe restricts this to less than 10 kiloamps, and the transverse probe is just 1.5 kiloamps, but still needs more work. BDOT probe says less than 30 kiloamps again, and we didn't have any Faraday rotation data because we tried to do this with the full energy, and we just blanked the glass completely. So finally, a quick discussion and some conclusions, because I think I have 5 minutes left. There are a few key differences between these experiments and some others. One is I lambda squared. It's lower for these experiments than those that measure some very high fields. Since we're operating and driving the plate with UV, that drops our I lambda squared significantly. That said, when I compare magnetic fields and currents across all the experiments and put up their I lambda squares, there's really no correlation as far as I can tell. That said, there's a lot of differences between experiments beyond I lambda squared. There's also been some very recent experiments on Vulcan that have corroborated our result done by Phil Bradford. And they performed their experiments in a similar dual proton probe geometry and basically the same intensity, but with 1 micron light. So they have about 10 times I lambda squared, and they found a very similar result where they saw this sort of transverse proton radiography bulge, but not very much current, and no rotation in the axial probe. Target construction and target stock placement vary across all these experiments significantly. So here's just 5 samples of different targets and what they look like. They vary a lot in quality. The target stock placement is sometimes on the driven plate, sometimes it's on the undriven plate, which is kind of surprising considering the initial motivation stemmed from drawing a current through a target stock. It seems like it would be important to place it on the right surface. And the targets have varying degrees of smoothness in their construction geometry, which could lead to a lot of electric fields if you're not careful. And finally, the ultimate problem with laser-driven coils is magnetizing the experiment. The fact of the matter is that the laser-driven coil is not independent from the experiment that is being magnetized. Driving the LDC creates a huge X-ray source that irradiates the target. And to keep fields high, inductance low, experiments have to be placed close to the driving plate interaction. So if you place a target really close to the laser-driven coil, it's going to be irradiated with X-rays, it's going to get preheated. You can try and shield your experiment, but I don't believe such attempts have been really successful. And what ends up happening actually is your shield becomes part of the circuit, so to speak, and creates a short circuit path typically, and you lose actually the current that you would have had going through the coil. And as you can see on this example, actually there's some blanking of this Faraday rotation medium even with the shield in place. So it's still not independent over here. It's and even if the laser-driven coil functioned as well as the most optimistic publication suggests, there are limitations. Since they have a very fast rise on the order of laser pulse, dB/dt is very high, and that leads to a very high induced EMF, which induces currents in the target if they're conductive. So if you try and magnetize a metallic target with a laser-driven coil, and you had 800 Tesla with a rise time of a nanosecond, that target's going to blow up before you can do anything with it. So that provides some more limitations on what you can do with laser-driven coils, even if they work. So let's revisit the question. How well do these laser-driven coils work? Not very well, and you would have to jump through these hoops. You have to have very efficient coupling to electrons just to make up for the energy to drive the field. I would suggest that you have a single plate laser-driven coil because we have not had any success with a double plate, and it seems like indirectly driving the other plate is a significant effect. And you have to keep the laser-driven coil small enough that inductance is kept low. The main experiment must be shielded from the X-rays from a kilojoule laser about 1 to 2 millimeters away. Your shielding has to be small though, so it doesn't become part of the circuit. And you also have to make sure your main target is small in size, because otherwise you'll have to magnetize more volume, which you don't have the energy for, and you have to make sure the target is non-conductive. And you also have to have an experiment where you don't mind if the field is non-uniform, and you don't mind if the experiment is preheated. And so with that, I will take any questions.
Thank you very much, Jonathan. I enjoyed your talk. If anybody has any questions, please enter them in the chat. And also, I invite everybody to unmute yourselves so we can give Jonathan a nice. I guess while people are typing anything in, I'll ask the first question. So what the state of the art is between distinguishing magnetic and electric fields?
I'm partial to the axial proton probe, but what I found on the most recent experiments is that when the current is low, if it's below 10 kiloamps, you can't actually tell too much with the axial probe. We created the axial probe because we were thinking if you have 100 Tesla, you sort of don't want to measure, you want to measure like a small portion of that. You don't want to measure all 100 Tesla in a way, which is what the transverse probe does. So I like the axial probe a lot. That's like my favorite one because it's pretty clear. The only difficulty I've found is that people maybe don't think it works because it seems unintuitive that putting protons parallel to the primary field causes a rotation. It's maybe not intuitive. But as we showed, it happens and exists. Eleanor Tubman.
Yeah, she says, really interesting results. Do you ever have to consider effects of the proton grid independently charging?
That's definitely something that does happen. And that's something that I would say that we haven't really gotten a good beat on. What was interesting is that those MyFEDS results, if I go back to them, really showed that sort of effect because MyFEDS isn't doing anything to the mesh in terms of focusing. But we see all sorts of smearing and focusing and weird effects when we go to the really low energy. Those could also be like electrons and X-rays depositing on the film, but that's definitely something that happens, and I haven't considered in terms of simulations. And I'm kind of stumped as to how I would begin to consider it when doing like proton probing simulations.
And there's a question from David Bishel says, are there other measurements that can disambiguate V and E fields of this magnitude?
The proton probe definitely feels like the best way so far that we have. I like the BDOT probes, but I feel like in order to make any sort of measurement that can distinguish between magnetic and electric fields, you have to have multiple probes, and you have to have a very simplified experiment because, I mean, simple as in you shoot a target on a stalk, like a foil on a stalk, and you put one probe on one side and you put one probe on the other, and measure the difference between the two. I mean, that's why we have the opposing loops in our probes to sort of help account for that effect, but I don't think it really succeeds on the whole. So I think you're going to have to just add more probes. That said, I still think that proton radiography is still going to be the winner, just because you can get the protons right through the region of interest, and you can't do that with any of these other diagnostics.
And Andrew Longman asks, could thing be used?
I have to imagine that it's been tried. Because I mean, if you went into an experiment and you said, "Oh, I have 800 Tesla field," I mean, that's kind of like I would use that to Zeeman split. But I have to imagine that it's been tried, is what I would say. We have not tried it, but I certainly think that you could make an attempt. But you do need to have quite a strong field to do that. And also can't have it be too hot.
Any other questions? Let's, oh, there we go. Spectral brightening tools, you need a really strong field.
Yeah, thanks, Dan.
Yeah. Heat and magnetic field. Okay.
Would a Rogowski coil work? I mean, the B-dot probe is sort of like a cousin to the Rogowski coil, so you could maybe put a Rogowski coil like around the stalk instead, and that would also give you a measurement. And there's no reason you couldn't beyond developing such a diagnostic. So I guess it also depends on the response time of the Rogowski coil. I don't know if they can respond that fast compared to the B-dot probe, considering we're trying to look at something that's changing sub-nanosecond levels. I don't know if a Rogowski coil exists that's going to respond that quickly.
Okay. Well, if there are no more questions, please unmute yourselves. We can thank our speaker again. Or Mingxing Wei got one in. Let's see. With short.
I tried to get into this with the I lambda squared discussion. This is something that Mingxing will find out in 4 days when I submit an LBS asking to do short pulse high intensity laser to try and drive field on the laser driven coil. I suspect that it will not drive, it definitely will not drive a persistent current, and it will definitely drive a strong electric field. I have to imagine it drives a very strong but brief, I don't know if you can call it a current, but wave of electrons. But there have been experiments where they proton probe, they shoot a proton probe and then bring the stalk in a sort of zigzag format back so that the probe is radiographing its own stalk, which is kind of neat. And you can watch a sort of current propagation wave through it. So there's definitely some interest there in terms of the details of how that works.
Okay. Unmute ourselves to thank our speaker again. And I hope everybody has a great rest of your Thursday, and see you guys next week.